Let's look at an example and see how does this work out. Maybe we get a better sense, hopefully, of what the story is there. Right? I will give you. Let me keep this a little lower so it's not mixed with what's going on there. We're gonna have one situation, one bar with a force applied to it, and see if we can use the principle of moments, find the moment about the point, and compare that with the typical way we do, finding the value for d. Example. Let's just go with find the moment, moment of the force. Let me bring the picture. If I can find it. I have it somewhere. Bear with me. There you go. Here's the picture. Force, you can add about 0.0, I guess, now that it's here. So it's more clear. Force about 0.0. Right? So forget about the principle of moment for the second, principle of moments, and let's go with what we know from before. Moment of force F, well, it's M is equal to FD. Now, what is F and what is D? Can someone tell me based on the figure that we have? Remember, this is the line of action, and this is the perpendicular distance. It's already shown that it's perpendicular there. There you go. So, what is F? What is D?
F is 5.
F is 5 kilonewtons, right? And what is D? I'll put 5,000 newtons to stay in. For units. What is D? To find D, look at this triangle. I cannot emphasize enough how important right triangles are in engineering generally, specifically in statics, dynamics, solid mechanics. It's amazingly practical and comes handy all the time. So if you look at this triangle right here, not the best color choosing. Okay. So if you look at this triangle right here, this is 75, this is 90. If you want, you can even find this one. This is 3 meters. We want to find this, D. What is D?
Three sine 75.
So here is the right triangle. Hopefully everybody's following, right? Just want to make sure that we're good. So this is the right triangle right there. This is 90, 75. This is 3, and this is what we're trying to find, right? So as Alex said, I think it was Alex, right? 75, if you say, let's just define both sine and cosine on this triangle. Cosine 75 degrees, d over 3. Sorry, well, let's just call this something. I don't know. Let's call this x. Where's sine 75 degrees? So sine would be what we have in front, which is d over hypotenuse. Cosine, what would we have? What we have as an adjacent, which is x over hypotenuse. So D would be 3 sine 75. Hopefully everyone gets where I'm going with this. 3.
Sorry, quick question. So whenever doing sine and cosine, you work around the opposite and adjacent from the right angle only?
So you can, so it, let's see if I understand your question. So you're saying if this is the right angle, and this is my triangle right there, right?
The opposite would be 3 and adjacent is x, or is it the other way?
So this is adjacent. Did I make a mistake somewhere? Okay, you know what? Let's just make it a little clear. It's not, I'm also confusing myself. So this is the right triangle. You have your x on this side. You have your hypotenuse is 3. So this is going to be opposite. Let me put it here. Opposite. This is going to be adjacent. So wherever your angle is, right? Hypotenuse is the longest side. That is clear. Now, find your angle, in this case 75 degrees. What is in front of it is opposite. What is next to it, which is not hypotenuse, is adjacent.
Okay.
Does that make sense?
Yeah, I guess I was looking at it weird. I don't know.
You can look at it this way, I think. Maybe it's more.
Yeah, I see it. Oh no, I just messed up. For some reason I was confusing. For some reason I thought the x and the d switched, like cosine.
Oh, all right.
D. Yeah, no, that's my bad. Sorry.
No. So you can also do it this way. You can just go with 75. You can go with 15 degrees here, and then say, well, if this is 15 degrees, this would be hypotenuse. 3 would be hypotenuse. Then hopefully I'm not making it confusing. This would be opposite. This would be adjacent. But then sine and cosine would have been switched.
Okay, I understand. Thank you.
So D becomes 3 sine 75 degrees. Right? Whatever that value is. Actually, don't have it calculated here. This is the first approach. Right? This is the approach we're familiar with. Find the line of action for the force and find the perpendicular distance between the line of action and the point O. All right. Now, let's see if we can look at it in a different way. I want to use principle of moments. I did this, so this becomes, I don't really have the number, but you can do the calculation. This becomes 5,000 times 3 sine 75 degrees, or whatever this turns out to be, Newton meters. Now, let's use principle of moments. I lost track. Let's call this approach 1. Call this, I can do the approach 1. Let's use principle of moments, and instead of finding D that we did here, let's decompose F into X and Y components and find the moment based using that. Right? Here's what I'm trying to say. Let's say approach D, approach 2. Now I want to use principle of moments. I do actually have the figure, so I can bring it up instead of me making it unclear. There you go. Here's what I did, or what the textbook did. So now instead of finding, well, M is the same, right? So what I do is that I'm going to decompose this force vector 5 kilonewton into two forces, Fx and Fy, and find the moment about O using principle of moments. Right? Now in this case, you have what? You have MO becomes M1, I'll write it this way, plus M2. Right? M1 caused by, or let's even do better, MX, MY. I have to be a little cautious about notation. So M, FX, you're gonna kill me at this one, but let me just be very clear. So let's do it this way. M, FX about O plus moment caused by Fy about O. Right? It's principle of moment. So these two moments, if I decompose the force into two forces, and then after you do that, forget about this. Right? This doesn't exist anymore. Now we have two forces. We have Fx in this direction, and we have to find this moment about point O. So if the line of action is this would be the distance for that, and that would be dy. So here you go. We say M Fx about point O is Fx, which is x component of F decomposed when we decompose F, and that is already calculated for us, 5 cosine 45 degrees in this triangle. Again, right triangles over and over are going to show up, this triangle. If this is F, that becomes Fx, which is 5 cosine 45 degrees. So Fx times the distance between, perpendicular distance between line of action and point O. So 5,000 cosine 45 degrees, right? F times D. The distance, well, if this is 3, another right triangle there, right? And this is 30 degrees. This distance becomes 330 degrees. 330 degrees. Now, is it positive or negative? The moment Fx create about point O, forget about this one. Is this moment, if we take clockwise as, just to remind you, we took counterclockwise as positive, right? And it's this way, and clockwise as negative, this way. So now, is this positive or negative?
It's negative because it's going to go down.
It's negative, exactly. So this is negative. This is negative. And I don't have the value for that. I'll leave it to you guys do the calculation. Now, MFY about point O. Now, let's look at Fy. Clean this up a little bit. Forget about Fx now. Fy. Oops, that was not supposed to happen. Here is Fy. Now we have Fy, this direction, which is 5,000 sine 45 degrees in that triangle. And here is the line of action, and this is the perpendicular distance. This is the line of action, and here is the perpendicular distance between the line of action and point O. So this is going to be your D. So this becomes 5,000 sine 45 degrees multiplied by, what is, well, you already know that. That's written there, so don't ask. 3 cosine 30 degrees. Is it positive or negative? 4 fingers in the direction of the force. So Fy is downward. This is 4 fingers along the force. The palm of your hand facing the point you're finding the moment about, make a fist. So it's clockwise. Since it's clockwise, it's negative. Newton meter, Newton meter. So once you know once you know moment because of Fx about 0.0 and moment because of Fy about 0.0, you can find M. Right? MO, you can find it. So what you find here as MO should be the same as this, the MO you find here. I'm going to write this MO. And we didn't talk about this. Is this negative or positive? Clockwise is negative, counterclockwise is positive. You should be very comfortable by this finding positive and negative by now. 4 fingers along the force, in this case F, the palm of your hand towards the point you're finding the moment about, make a fist clockwise. So that's negative, whatever value it gives. Question so far. So I'm solving the same problem, different approaches. First approach, I said, well, let's find the perpendicular distance the line of action of F has to 0.0. I'm finding that I'm finding the moment about D. Use geometry, found that D. Second approach, I said, let's use principle of moments, decompose the force into X and Y components, and then we are going to have a system of forces, Fx. So system of forces for moments. The final moment or resultant moment would be the summation of all the moments that those forces create about the point we're finding the moment about. Right? And in this case, both of them turn out to be negative. So basically, the final answer is negative, the same magnitude as those summation of those two magnitudes. Negative something here, Newton. All right. No question. All right. I might actually be able to find the answer here. So give me a second. I can even give you the answer. This, I believe, becomes. I'm going to double check this after the class and fix it on the slide if it's not. But I believe this is 14.5 times 10 to 3 Newton meter negative. Or you can just write it 14.5 times 10 to 3 this direction. Either you should show the direction or you should put the sign. This one gives you the same thing. Minus 14.5 10 to 3 Newton meters. All right. So, is there any other way I can solve this? There is actually another approach that still includes principle of moments, but instead of decomposing this into these two vectors, right? I took this as X direction, and I took this as Y direction, and I found the components in these directions and multiplied the values. Found the values by multiplying the force magnitude in that direction and the perpendicular distance for each one. There is a third approach that it's still principle of moments, but decomposing the forces can be done along different axes. I can do this. Approach 3. Here's what we can do. I'm going to bring in the picture for that. If I can find it. There you go. Here's the third approach. This time we took this as x. And I can think about this as y. Or direction doesn't really play a role in this case, but let's just avoid confusion. I take the positive as, I take this as x and y. Right. And again, just to make it clear, I'll keep it where everything else is. So this is x, this is y. Now in this case, this is x, this is y. The same story. Now, moment about point O, when I decompose this force vector into two components along these x and y, goes back to what I was just saying about the slab on a surface, on a tilted surface. Coordinate system is what you decide. You can tell me, here is my coordinate system. Based on this coordinate system, here are the results. It's the same story here. You change the coordinate system from x, y, being horizontal and vertical, like along the horizon, and y perpendicular to that, to x being along this rod or piece of wood, whatever it is, and y being perpendicular to that direction. Only thing changes is that now the components of the force on x and y axis change, right? But the moment of this force about point O by the end of the day doesn't change. M O again is mfx about point O plus mfy about point O. So mfx, moment caused by fx about point O, is, so what is fx? I have to multiply fx by the distance, perpendicular distance of fx and point O. Here is fx. Here is fx, and this is the value for that. This is the line of action for fx. What is the moment of fx about point O? The moment fx creates about point O. This is something I just mentioned at the beginning of this lecture.
Is it the 5k cosine 75?
All right. So follow the line of action. It's the green line. Fx, the force is 5,000 cosine 75 degrees. What
Would
is
it
D?
be 0 because it's a line of
Exactly, Diego. Exactly. So because the line of action is passing through the point we're finding the moment about, that's 0. You want to be more technical, write it this way. 5,000 cosine 75 degrees times 0. Why? Because the distance, there is no distance here. This line is passing through point O. There is no perpendicular distance. So this component does not create any moment. MFY about point O, moment of force in the y direction about point O. We have, here is FY. I really have to be more aware of what color I'm using. So here is FY. Here is the line of action for Fy. I know the magnitude of Fy is 5,000 sine 75 degrees. Right. Now, what is the perpendicular distance between the line of action for force Fy and point O, we're finding a moment about. What is D?
Is it just 3?
It's 3, exactly. So that becomes 3 times 3. Now this, and is it positive or negative?
Negative?
Negative, exactly. So this is negative. Let's just keep it here, Newton meter. Then as a result, you get MO. If you sum these two up, let me just double check the number, at least on this one. If they're wrong, I'll fix it later on, but sine 75 times 3, 14.5. Yeah, that's approximately correct. This becomes 14.5 times 10 to 3. It's 14.48, but I'm just rounding up all of it. It's negative Newton meter. Or you can write it this way, 14.5 times 10 to 3 Newton meter clockwise.